Matrix notation is one of those things that can look more intimidating than it really is. But the good news is that nothing fundamental about OLS changes here. We are not learning a different estimator. We are learning a cleaner language for writing the same estimator. And once you see that, a lot of econometrics becomes easier to organize. In this episode, I want to show you how the familiar multiple regression model gets packed into vectors and matrices, how the OLS formula drops out in a neat compact form, and why the matrix version makes unbiasedness, variance, and blue much easier to see. So why bother with matrix notation at all? Mainly because it scales better. In scalar notation, every extra regressor adds another symbol, another summation, and another line of algebra. In matrix notation, all of that gets compressed. Instead of writing equations observation by observation, we stack the whole sample together and treat it as one object. That is incredibly useful once regressions get more complicated. It also becomes the standard language for later topics like generalized least squares, instrumental variables, and panel data. So this is really about building fluency, not changing the underlying economics. Let us start with the usual regression for one observation. We write y sub I as beta 0 plus beta 1x1 sub I, all the way up to beta k xk sub I plus u sub I. Now we bundle the regressors for that observation into a row vector x sub I. The first entry is 1 because we are including an intercept. Then we stack all the coefficients into a single column vector beta. This is the first important move. Instead of thinking about one coefficient at a time, we now treat the full parameter list as one mathematical object. We do the same thing for the whole sample. The dependent variable becomes a column vector y. The error terms become a column vector u. And the explanatory variables become the matrix X, whose rows are the individual observation vectors x sub I. So X has n rows, one for each observation, and k plus 1 columns, one for the intercept and k more for the regressors. Once that structure is in place, we can write the whole sample model in one shot, instead of writing n separate equations. That column of ones deserves a quick pause, because it explains a lot. It is there only because we included an intercept, and it also helps explain the dummy variable trap. If you include a full set of mutually exclusive dummies along with the intercept, those dummies add up exactly to the column of ones. That means one column of x can be written as a combination of the others. In plain English, the data no longer contain enough independent information to separate all the coefficients. That is perfect collinearity in matrix language. Now we can write the model in its compact form, y equals x beta plus u. That one line represents the entire regression system. Y is the observed outcome vector. X beta is the systematic part predicted by the regressors, and u is everything left over. One reason this form is so useful is dimensional discipline. X is n by k plus 1. Beta is k plus 1 by 1. So the product x beta is n by 1, which lines up perfectly with y. Once you get used to checking dimensions, matrix algebra becomes much less mysterious. How do we get OLS from here? The same way as before. We choose beta hat to minimize the sum of squared residuals. When we take first order conditions, the matrix version becomes x prime times y minus x beta hat equals 0. Rearranging gives x prime y equals x prime x beta hat. These are the normal equations. If that sounds fancy, do not let the label distract you. It is the same idea we already had in scalar notation. The residuals have to be orthogonal to the regressors at the optimum. If x prime x is invertible, we can solve directly for beta hat. The result is beta hat equals x prime x inverse times x prime y. That is the matrix formula for the OLS estimator. And the invertibility condition tells us exactly what can go wrong. If the columns of x are not linearly independent, then x prime x has no inverse, and the estimator is not uniquely pinned down. So the no perfect collinearity assumption is not just a nice extra condition. It is what lets the algebra actually produce a usable estimator. Once beta hat is in hand, the fitted values are just y hat equals x beta hat. The residual vector is y minus y hat, which is y minus x beta hat. Here, matrix notation gives us another clean payoff. because the first order conditions say x prime u hat equals 0. We immediately know the residuals are orthogonal to every included regressor. Since the intercept column is part of x, this also tells us the residuals sum to 0. So all the sample moment results we saw earlier are still present. They are just written more elegantly. The assumptions also become compact. We still need linearity in parameters. We still need no perfect collinearity, which in matrix language means x has full rank k plus 1. And we still need the exogeneity condition, now written as E of u given x equals 0. That notation is useful because it says the whole error vector has conditional mean 0 once we condition on the whole design matrix. In other words, none of the included regressors should have systematic leftover correlation with the unobserved part of the model. The unbiasedness proof now becomes very short. Start from the OLS formula and substitute in y equals x beta plus u. Then beta hat becomes beta plus x prime x inverse x prime u. Now condition on x. The first term is just beta. The second term contains E of u given x. Under the 0 conditional mean assumption, that part is 0. So we get E of beta hat given x equals beta. This is one of the nicest things about matrix notation. A proof that can feel cluttered in scalar form suddenly becomes very transparent. Under homoskedasticity and no serial correlation, the error covariance matrix is sigma squared times the identity matrix. Once you plug that into the variance expression for beta hat, everything collapses neatly, and you get var of beta hat given x equals sigma squared times x prime x inverse. Again, same content as before, just cleaner packaging. The precision of OLS depends on the scale of the error variance and on the geometry of the regressor matrix. More independent information in X means a tighter inverse matrix and therefore more precise coefficient estimates. The blue result also looks cleaner in matrix language. Any linear estimator can be written as a prime y for some matrix A. If that estimator is unbiased, then A prime x has to equal the identity matrix. From there, we compare its variance to the variance of OLS. The difference can be written in a form that is positive semi-definite. That sounds technical, but the intuition is simple. OLS is squeezing as much precision as possible out of the data while remaining linear and unbiased. So no other linear unbiased estimator can beat it on variance. So the big takeaway is not that matrix notation changes econometrics. It does not. The big takeaway is that it gives us a better operating system for econometrics. The model becomes y equals x beta plus u. The estimator becomes beta hat equals x prime x inverse x prime y. The assumptions, the unbiasedness proof, the variance formula, and the blue result all become easier to organize. Once this notation feels natural, later topics stop looking like disconnected tricks and start feeling like extensions of one coherent framework. Matrix notation is really just a more powerful way of expressing ideas you already know. It turns long strings of regression algebra into a compact system you can reason with more easily. Next, we switch from algebra to practice and talk about data and specification, which is where model choices start to matter just as much as formulas.